Hi, and welcome to a discussion for Homework 3 for statistical inference. So the first question asks to load the dataset empty cars in the datasets package and calculate a 95% interval for the miles per gallon for the variable miles per gallon. So calculate an interval to the nearest mile per gallon. So we want to make sure that we do library datasets, and then we do data empty cars, and then we can do head empty cars just to see the top of the data set. Miles per gallon is the first variable. I'm going to attach the empty cars data set just so that I don't have to type the $sign. So for example, if I wanted mean MPG now, I would just type mean. The average across all the car types was 20.1 miles per gallon, and the standard deviation of MPG was 6 miles per gallon. So if I were to do Ttest of MPG, that would give me my T interval. If I just want to grab the conf.int part of it, then it'll just give me my confidence interval. And then if I want to round that to the nearest decimal place, or round it to the nearest mile per gallon, there it is, 18 to 22. So I'm going to try 18 there, and I'm going to try 22 there, and I'm going to click submit, and they're both correct.
Suppose that the standard deviation of 9 paired differences is 1. What would the average difference have to be so that the lower endpoint of a 95% student's t-confidence interval touches 0? So in this case, I just wrote out n is 9, standard deviation is 1, and they're paired differences. So what that means is we had pairs of measurements, like let's say a baseline and a follow-up measurement, and we subtracted them. That's what we do when we have paired differences. And so the idea of the paired difference interval would be the average difference plus or minus the appropriate t quantile, right, the 0.975th t quantile, times the standard deviation, which is 1, divided by square root n, which is square root 9, which is 3. Okay, so just to remind ourselves, the appropriate t quantile is the 1, so that 2.5% lies above it, and 2.5% would lie below the negative of it. So this would be t 0.975, and then the degrees of freedom are the n minus 1, so the degrees of freedom are 8. So I could just write t 0.975, Okay, and so we're interested in the lower endpoint, so let's just forget about that plus, because that'll give us the upper endpoint, so that's the lower endpoint, and we want to know when that touches 0. Okay, so the average would have to be y bar has to be equal to t times the 0.975th quantile divided by 3. So we just need to figure out what the 0.975th quantile is and divide it by 3. So let's go ahead and do that. I have RStudio open, so I want QT 0.975, but remember the t distribution also has its degrees of freedom. Its degrees of freedom is 8, and we don't want to divide that by 3. So it says it should be around 0.77. Okay, so let's go back to our web page and type in 0.77 and submit. And there's the check mark. I think we can just talk our way through this next one. Basically, the question asks if you understand the difference between paired and unpaired data analysis. We cover this very much so in the lecture. If our observations are paired, then we're going to do a paired t-test, and if our observations come from groups that are naturally assumed to be independent, then it's going to be an independent group t-test. And I just want to comment that if your data are paired and you treat them as if they are independent, then you're going to potentially get very incorrect conclusions, a very incorrect interval. On the other hand, if you do a paired interval when you're in fact your groups are independent, then that's just unreasonably incorrect. That's so incorrect. There's no, you can't even plead ignorance in that setting. Okay, so probably the most common mistake is to treat paired data as if it's independent, and the most common consequence of doing that, it depends a little bit on the circumstance, but the most common consequence of that is that variability that's explained by the pairing has been left in the interval, and you're getting an interval that tends to be wider than what you would expect to get otherwise. So that's the consequence of that. You're pretending like you have uncertainty that you don't have, which is unfortunate because you get a wider, less precise interval. Okay, so let's do that, and then we get our check mark. So the next question is just asking us, can we do a t-test comparing two groups using R? And it asks us to take the MT cars data set and compare 4 and 6 cylinder cars using a t-test with a constant variance. So let's do head MT cars just to show us what it looks like. So I want, let's say my 4-cylinder, I'll just is MT cars miles per gallon, which is what our outcome is. In the case where MT cars $$ cylinder equals 4, and it probably if you're doing this now, you probably want to use dplyr, which is better for working with data frames like this. But those of us that have been using R for a long time have kind of gotten used to doing things this old school way, but probably you want to use dplyr. Probably make this like one command instead of two. Okay, now we want t.test C4 C6, and I want var.equal as true because the problem specified an equal variance test. And there you see it's 3.15 to 10.69. Okay, so let's put it in. We want 3.15 to 10.69. Submit. There we go. Okay.